We're now going to talk about the ellipsoid algorithm, which is really a fundamental and was the original proof or the cornerstone to the original proof that linear programming belongs to the set of polynomially solvable problems. But as we're going to see, it is a tool that's useful far outside of that for theoretical problems, and in particular showing for theoretical complexity results. So it was the first, because simplex was not known to be in polynomial time algorithm, because you could potentially need to do exponential number of these pivots, even for non-degenerate problems. It was not known before the ellipsoid algorithm whether even small linear programs where you didn't need, where you could just explicitly write down the constraints and check feasibility and find violation, etc., was a polynomial time problem. But we're going to see that ellipsoid algorithm solves much beyond that. So let's talk about the fundamental problem, the basic problem, which is that of finding a feasible point. So here's a setting. We're given a polytope P, which is equal to x in Rn that satisfies that has to satisfy some number of inequality constraints, I equals 1 to m. And though all of these assumptions that I'm going to put down now can be removed with some additional work, for this exposition we'll leave them in place. So we're going to assume for now, and what I mean by for now is that these can be removed with additional work, that P is bounded, and if it's non-empty, it is full dimensional. So no equality constraints. Again, all of these things can be removed. And what we must do is, our goal is in time that's polynomial in the dimension n and the description length and I will denote this in this way. The description length of a scalar or a vector or a matrix, I'll use these brackets, these angle brackets, to denote the number of bits needed to specify it. So in particular, I'm assuming that everything in sight is a rational number. So the description length of A and B decide between decide first of all, is P empty or not? And if you decide that it is not empty, then you must produce a point in P. If non-empty, you must produce a point in P. So this is the problem that we want to solve. So let's give the basic, let's say, proto-framework for the ellipsoid algorithm, and we're going to use that to then see what are the holes that we need to fill in order to make this into an algorithm. So here's the idea. So suppose, first of all, that we have an oracle and this oracle takes a point x and reports that it is feasible or it provides a violated constraint, which I'll just denote by A0, which is the vector, and B0, which is, let's say, violated constraint, meaning a constraint violated by x. And let us also suppose that initially we know a bounding sphere. So we know a sphere that contains our polytope. So suppose initially we know that our polytope is contained in a ball centered around, say, the origin. This is not that important, of some radius, r squared. And let's also suppose we know that if P is non-empty, then its volume is lower bounded by some number. And this number is going to be 2 to the minus n plus 1 times the description length of A plus n cubed. You'll see where these numbers come from. And you'll see that it turns out that these assumptions are not really assumptions. There are things that we'll be able to hold. But I'm writing suppose just so that we don't have to worry about whether I could just have written them as a lemma. That we can compute R and can compute this lower, or prove this lower bound, assuming that P is non-empty. So I should actually write that this is true if P is non-empty. So it's allowed to be empty, but if it's not empty, it must have volume that's lower bounded by this. So this is how the ellipsoid algorithm is going to proceed. It's going to maintain a set of ellipsoids that contain what we know is the feasible set. And currently, initially, all we know is that P is contained in this ball of radius r squared centered around the origin. So we're going to initialize our algorithm by the first ellipsoid, E for ellipsoid, E0, because we're initializing it, is going to be B0 r squared. It's promised us by the assumptions. And I'm going to we're going to talk about how we encode or how we describe ellipses, but briefly we're going to talk about the details. But borrowing from what's going to come in the future, we're going to describe an ellipsoid by essentially the linear transformation that transforms the unit ball into that ellipsoid. So the unit ball just needs to be we get the unit ball by we get the unit ball of radius r squared by just taking we get the ball of radius r squared by taking the unit ball and multiplying it by r squared. And it's again centered around the origin. So this notation, don't worry about it for the meantime. It's just that a matrix A0 and a vector A0. Is this a notation I've used? It seems a bit overloaded. Encodes any ellipsoid. We're going to go over these in detail soon. So we initialize with an ellipsoid that we're guaranteed contains our ball, and we take, okay, let me write this as x0, and we take the center. This is the center point. We take the center point and we feed it to our oracle and say, is this feasible? If the answer is yes, then we're done. We've solved our problem. We've found a feasible point. So so this is what we do at iteration k. At iteration k, what we have is an ellipsoid which we'll call EK, the kth ellipsoid, which again is going to be defined by a matrix, which I'll call AK. Note that I've overloaded A here, but I hope it'll be clear from context. So AK has nothing to do with the constraints that define P now. It's just the affine transformation that defines the ellipsoid. With center XK. So at iteration K, this is what we've got. We've got our ellipsoid EK that's defined by matrix AK, and this is its center. And it goes to the oracle, and it gives the center. So we give XK to the oracle. And what could happen? If the oracle says XK is in P, it's feasible, then we stop and we've solved the problem. Otherwise, what do we do? Well, otherwise the oracle is going to provide us with an inequality which cuts our ellipsoid, which makes our ellipsoid smaller. It's provided us some information. So otherwise what we do is we find a new ellipsoid, EK plus 1, that contains the largest possible set that we know of so far that contains P. And what is that? That's where we were previously, that ellipsoid EK, intersect the half space that the oracle gives us. So the oracle reports back this half space defined by, let's just say, A hat transpose X less than B hat. That's what the oracle gives us, this inequality. And note that this intersection has to contain P. Again, let's see why that is. It's because the algorithm, by definition of the algorithm that we're giving so far, or proto-algorithm, or whatever we should call this, creates this set of ellipsoids which at every stage contain P by assumption. We feed the center point to the algorithm, to the oracle. If it's in P, then if the oracle says you're in P, then we're done. But if not, the oracle provides us a half space where P is on one side of that half space. So therefore, if we know that P is on the one side of the half space, and we also know that P is in EK, then P is also contained in the intersection. So we have this intersection here that contains P, and we're going to try to find the tightest ellipsoid we can around it, EK plus 1, and we repeat. So what this is basically doing is it is going to corner. It's going to try to find smaller and smaller sets that contain our ellipsoid. So let's just kind of see what the picture is here. So by picture, what we've spelled out so far is that there is some polytope given by these extreme points, and all we originally know. So this is the set, and our goal is to find something in there. Now, all we originally know is that this is contained in this set around the origin. And so we ping the oracle and we say, is the center in P? And in this example, the oracle would say, no, it's not in P. But it doesn't just say no, it also provides us an inequality. So if it provides us with an inequality, that inequality is going to be something like this. And it tells us that the polytope is on this side. And so then what we're going to do is we're going to find another, we're going to find a new ellipsoid. And what is that new ellipsoid going to look like? It's going to look something like this. Oops, sorry, bad drawing. And what did it have to do? It had to contain the intersection of our previous ellipsoid with the half space. That's what's written here. The intersection of our previous ellipsoid with the half space. And if it does that, just like the picture shows, it has to contain this polytope. So let's reason. What are the missing holes now? Let's review this and think. what are the missing holes that we need to plug in order for this to turn this kind of very loose idea into a specific algorithm. So the key idea that we need is we need an efficient way to find ek plus 1. Let me just, so this is my ek, and this new one would be ek plus 1. We need a way to find ek plus 1, and we want it to, we want ek plus 1 and ek to have the relationship that's suggested by this picture, namely a significant shrinkage of volume. So we need a way to find ek plus 1 to guarantee that its volume shrinks quickly enough. What does quickly enough mean? Well, if, for example, you could show that it shrinks by a constant factor every time, then let me flip back and see what, now you can see why we had assumption B here. If we know that there's a lower bound on the volume, and we know that we have an efficient procedure that is able to find smaller and smaller ellipsoids whose volume, when I say smaller and smaller, their volume is shrinking by, say, some factor, some constant factor every time, then this tells us that before a very large number of steps, within only a polynomial number of steps, we would have an ellipsoid which has two promises now. First, it's guaranteed to contain the set P and also has a very, very small volume. If that volume is below this, that is a certificate that our set P is empty. So this is what's going to happen. So in words, the ellipsoid algorithm is going to find, has an ellipsoid ek with some center. It queries an oracle. Is this center in the set? If the oracle says no, it provides an inequality that's violated. We now find an ellipsoid that contains that sliced ellipsoid, the half that's left over, and it's going to have a center point. So maybe in this case, just visually, that would be the center point. We feed that point to the oracle, and in this case, the oracle says you have succeeded, and so we're done. So this is what we need to do, and basically what we need to be able to do is to find ellipsoids. So we need to now put on the brakes a little bit and define kind of key properties that we need in terms of ellipsoids. So we're going to do the following. We're going to give a definition that is important and useful far outside just the ellipsoid algorithm, but it is the key definition that we need. So let's start with a theorem that says the following: if K is any convex subset of Rn, then there exists a unique minimum volume ellipsoid E that contains K. Moreover, this ellipsoid has a special property that if you shrink it from its center by a factor of n, it must be contained in the set K. And so the Löwner-John ellipsoid is defined as this smallest ellipsoid, and this theorem guarantees us that it is that this is well defined. Let me write out the second property that I mentioned. So moreover, our convex set K, and you can see also that convexity is required. Otherwise, if you just have 4 points, then an ellipsoid, the smallest ellipsoid that contains them, the shrinkage of that ellipsoid will not be contained course, those 4 points. So moreover, K contains, I'll put this in quotes to explain, and I'll explain what I mean, where 1 over n e is the shrinkage of E with respect to its center. So in other words, translate E to the origin, multiply by 1 over n, and then translate it back. That's what this operation does. So this is called the Löwner-John ellipsoid of a set K. And for a general convex set K, this is hard to compute, although in many cases we can approximate it. The key part of the ellipsoid algorithm is that the Löwner-John ellipsoid of the intersection of an ellipsoid and a half space is in fact very straightforward to compute, and we're going to show what that computation is. So for a general convex K, the Löwner-John ellipsoid may be hard to compute. But we will see in the next lecture that when K is equal to the intersection of an ellipsoid and a half space, the Löwner-John ellipsoid of K is easy to compute. In the next lecture, we're going to be a little bit more careful in talking about how we define ellipsoids, how they're parametrized. I've kind of referred to that in 2 slides prior. And then we're going to show what the explicit form is of the Löwner-John ellipsoid that contains this intersection of an ellipsoid and a half space. And we're going to go through the key elements that we need in order to make the ellipsoid algorithm work, namely showing that we in fact have this volume reduction, which is important. So we're going to pick this up in the next lecture.